Hi all. Today we discuss section 2.5 row space of a matrix. We start with an m by n matrix. Let A belongs to m by n of over R. That means this is the an arbitrary m by n matrix. So this we can assume this A is equal to this A should have m rows and n columns. Say A11, A12, etc. A1n, A21, A22, etc. A to n, and finally we have mth row AM1, AM2, etc. AMN. So these are the m rows of A or the entries of A. Then we can define R1 or R1 as R1 is equal to A11, A12, etc. A1n. So each row can be considered as a 1 by n matrix. So similarly R2, you can define R2. R2 is A21, A22, etc. A to n. Similarly, the last one Rm is equal to AM1, AM2, etc. AMN. So these are all elements of Rn, because these Aij's comes from this Aij belongs to R. So each of these are real numbers. So this is an element of Rn. Each of these elements is an element of Rn. It belongs to Rn. Now this constitutes a subset of Rn. That is, say S is equal to I'll write that set as set of all R1, R2, etc. Rn. We call this set as S, and we consider this always a subset of Rn, because these are all elements of Rn. Now consider the span of this S. Span S, that means the set of all linear combination of elements of this set S, that is C1 R1 plus etc. Cm. So this we have m rows, so we have m here, Cm Rm. Okay, these are the span of S. This is always a subspace of Rn, and the subspace is called row space of A. Okay, this is a subspace of Rn called row space of A. Row space of and this the dimension of this row space, we know that dimension of span of S is always less than or equal to n, which is the dimension of Rn. So since this is a subspace, then the dimension is always less than or equal to this, and this dimension, this is what we called row rank of A. Row rank of A is the dimension of the row space of A. The row space of A is the subspace spanned by rows of A in Rn. Okay, so this is the definition, and we have an example. We consider A is equal to the matrix 1, 2, 3, 4, 5, 6. So this is our matrix A, and we consider the first two rows 1, 2, 3 and 4, 5, 6. So this spans the row space. Okay, span of this is called the row space of A, is the row space. Right, this is a row space, and since this is linearly independent, then row rank of A is 2. Okay, so this is the example. Now we will consider the some typical cases. For example, A is a row reduced recurrent matrix and all. Consider a matrix A, say some 1, 2, 3, 0, 5, 2, and we have 0, 0, 0, 0, 3, 0, and this is going to be the matrix R, and this matrix has this property. The only non-zero rows, I'll put one more row here. This is the 0th row, and since this has three rows, and first and second row are non-zero rows, so that comes in the first section of the matrix, and all 0 rows come under the these non-zero rows. And if you consider the first row, the important property is the leading entry of the first row is 1 here, okay, and leading entry of the second row is also, leading entry of all the non-zero rows is 1 here. This is 1 and this is 3, okay. If this leading entry is not 3, so we call this is not a row reduced echelon matrix, okay. So first of all, we are going to define what is row reduced echelon matrix. That is, the first property should be all the non-zero rows comes the first part of the matrix, and all zero rows are come under the these non-zero rows. And if you consider the first non-zero row and the leading entry of the first non-zero row should be 1 here, then we consider the second row. If you consider the second row, the second leading entry should be 1, okay. So if this were 1, we can say that these two rows has this property, the leading entry should be 1. And once you got this idea, we can get the all the entries in that column, the corresponding column should be 0, okay. If this is 1 here, then this should be 0 and this would be 0. Here we need to put this is 0, okay. Then if you consider a matrix of this form, a matrix is 1 2 3 0 0 2, and the second row is 0 0 0 0 1 and 0 and 0 0 0. This we can say that this is in the row of the form row reduced echelon matrix, okay. So this is an example of a row reduced echelon matrix. Consider the first row and the leading entry should be 1, and consider the second row, the leading entry should be again 1, and this is a 0th row. For all non-zero row, we should have the leading entry in the first entry. Leading entry is the 1, okay, and all the entries in that the corresponding column of leading entry should be 0. Here we have 0, here we have 0, here these two quantities are 0, okay. So this is the requirement of, and if we can say that R1 is a row reduced echelon matrix with the first non-zero rows, this is the first non-zero row, and this comes under first column, this is the first column, and this is in the fifth column, okay. So we can say that if you write the matrix like this, 0 0 0 0 1 0 and 0 1 1 2 3 0 0 2 and 0 0 0. This is not in the row reduced echelon form, because if you consider this matrix, we can say that the leading entry is always 1 here, here also 1, but the leading entry of the first row comes in the fifth column, and corresponding to the second is the, so if we have r non-zero rows, then we need to name it like this, 1 2 3 etc. are the first r non-zero rows of this row reduced echelon matrix, and the first leading entry of the first row comes in the k1th column, and leading entry of the second non-zero row comes in the k2th column, and here k3th column etc. krth column, and we should have this k1 should be less than k2 less than etc. less than kr, okay. In this, if for this matrix we have 1 2 only 2 non-zero rows, and the first leading entry of the first row comes in the fifth column, so this k1 is 5 here, this is k1, and in the case of second we have 1, okay, so this is k2, so we cannot say that k1 is less than k2, okay. So this is not possible, so this is not a row reduced echelon matrix. But in this case we have again 2 non-zero rows, but the leading entry of the first row comes in the first column, so k1 is this is the suffix of the column, and the second row we have the leading entry comes in the fifth column, so we put K2 as 5 here. Okay, now we have K1 is less than K2. So this is of the this matrix is an example of row reduced echelon matrix. So next so we have K1 less than K2 here, and in the next class we will we will prove that for a row reduced echelon matrix, if you consider this is the row reduced echelon matrix and the row space of this R1 is obtained by the span span of this rows, and we will prove that these two rows form a basis for the row space of this R1. That means the row rank of this R1 should be the number of non-zero rows in this collection. So in this case we can easily say that if this is in the row reduced echelon form, then we can say that the rank of row rank of R1 is the non-zero rows of this. So that is 1, 2, 3. These two are non-zero rows, then the rank is 2. Okay, so this is the easiest way of getting rank of a matrix. So in order to get a rank of a matrix, suppose first suppose that that is in the row reduced echelon form. Otherwise we will prove that in the later case we will prove that any m by n matrix can be equivalent to a row reduced echelon matrix, and we prove that the row reduced equivalent matrices should have the same rank. So we can extend this theorem to a an arbitrary matrix A. If A is to find the rank of A, first you reduce that into the row reduced echelon matrix and just count the non-zero rows of that matrix. That will be the rank of row reduced echelon matrix. And later we will prove the row rank of a row reduced echelon matrix is same as the row rank of the original matrix. So in the next class we will prove that theorem.